All of you. Welcome to this class on the series of aerodynamics lessons. And hope we have gone through our lesson on the atmosphere in general and the aerofoil structure and the definitions which I've already put. These were preparatory, and there is another important subject or lesson which works as a preparatory lesson is to learn about the particles, the air particles in the atmosphere, and basic definitions, and so that it goes a long way in understanding the several theories explaining different aerodynamic phenomena. So this is a little bit of a very basic preliminary lesson. May not be that interesting, but nevertheless it's important uh, for us to understand several other concepts as we proceed on this particular subject of aerodynamics. As we proceed on this subject of this airflow, that's what we are going to learn a little bit in more detail in the next 2 3 lessons. Airflow. Before we consider airflow in total, let's understand how the airflow is going to be explained. Here in this diagram, I have magnified a section of one a string of an air flow stream uh, where I have shown the particles. So this is called the path of the particle, that each particle uh, following a particular path in that particular airflow. So as you see the diagram below, it's not necessarily it need be a straight line, it can be a curved line. So at any point the path of the particle is tangential to the curve and or the surface of the curve. So that's the definition of the path of the particle. Okay, let us get on to some serious definitions on this airflow theory. Um, when I was young, when I was undergoing all these classes, these classes were never considered very important, and I think we usually skipped these classes and learnt only the preliminary. And there were several doubts which lingered in our minds for a very long time before we actually learnt it ourselves. Therefore, it is very important for us to understand this, the critical aspects of these definitions, which I am going to enumerate. Anyway, the first definition which I would like to introduce you is the streamline. It is the path traced by a particle in a steady fluid flow. Series of particle flow forms a stream of flow. The entire flow is represented by series of lines called the streamlines. It follows from this definition that through every point in the field there passes one and only one streamline. There is one exceptional case in which where a streamline may intercept itself, that is at the point in the flow where the local velocity becomes zero, which we are going to learn about this. It is called the stagnation point, which we will learn about it uh, and the phenomena of it. But for for now, I think this definition is very clear. The streamline is series of particle which doesn't collide with each other. It just follows one after another in a particular manner. So there is no collision, there is no interaction between each other. So what is important? It can be represented as a line, and they don't intersect with each other. Okay, here I have shown a curved streamline. Sometimes we incorrectly interpret that streamlines have to be in a straight line. Not necessarily so. It can be curved, and as I have shown, even in a curved path, it can well follow the rules of a streamline. That means it need not interact with each other, and it can follow like a stream. So that's what I have tried to explain so that the concept is very, very clear here. Okay, next is a very important definition in my opinion. That's the stream tube. Just imagine a circle in middle of the atmosphere, and uh, it gets extended and it follows and forms a kind of a tube. Any flow during through this tube, uh, or the flow pattern which forms such a tube is called the stream tube. Now, it need not be of uniform cross section. The tube itself may vary in cross section. Therefore, the thickness of the or the distance between the streamlines may vary accordingly, which is what I have tried to show in this diagram. Initially on the left, it's a big circle, and thereafter it's gradually narrows into a small circle, and the stream lines are passing through this tube. It's an imaginary tube. It's 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 uh, it's the path followed by a set of uh, a group of or set of stream lines. So let's understand, if all streamlines passing through the points on this curve are drawn, then they generate a tubular surface which is called the stream tube. That means from this circle, if when the stream filaments are flowing, then it is called a stream tube. Now, stream filament, this is a single stream tube of infinitesimal cross section. That means smallest, one single particular kind of a filament. That's what we call stream filament. Okay, let's define something called steady streamline flow. The flow parameters, that means the speed, direction, pressure, may vary from point to point in a flow. That means between two points on the flow, it may vary. But at any point, it's constant with respect to time. It can be represented by streams and is the type of the flow. Steady streamline flow may be divided into two types, which we are going to see. Okay, what do you mean by a constant with respect to time? That means you measure the parameters now, and after another 5 seconds you measure the parameter. After another 10 seconds you measure the parameter. At all different times, the parameters are going to remain same. That's what I mean by constant with respect to time. But nevertheless, in the flow, you take it at a point A and at a point B. They could be differing. That's what is the point of this particular characteristic. Okay, next definition is a classic linear flow. This is the basic flow pattern which we will encounter in our studies, and classic linear flow is found over a conventional aerofoil at low angles of attack, in which the streamlines more or less follow the contour of the air or of the body, and there is no separation. And when it comes to an end, it joins back, and it resumes its normal state. status. That means at 2 points below, well above the ahead of the aerofoil and well aft of the aerofoil, there's absolutely no disturbance in the airflow. This is called the steady streamline classic linear flow. Okay, here is something very interesting. There is another type of flow which is called the leading edge vortex. Uh, it's a controlled, separated flow. It is halfway stage between a steady streamline flow and an unsteady airflow, which we are going to describe later. The flow separates from the surface, but it doesn't break down into turbulent or chaotic condition, but instead forms a strong vortex when which, because of its stability and predictability, can be controlled, and it is made to give very useful lift force in some wing platforms such as delta and swept back platforms. These are very useful in high speed flights. So we are going to study it in detail as and when we come across that uh, particular kind of wing platforms and airflows around it. Here I have shown a diagram to indicate how this particular leading edge vortex flow will be. Here I have shown a wing and the airflow. It starts with a small circular whirl at the wing root and grows gradually into a bigger circle and bigger vertex, and then smoothly flows out. It's a very well controlled kind of flow. It's not the laminar classic flow, but it's a very controlled flow, and it's sometimes in some phases of flight it's going to be useful. So that's what we need to understand. And last but not the least is, of course, unsteady or unsteady flow or turbulent flow, as I have shown. I've shown in a diagram in which a cylinder or a sphere around which an airflow is taking place. Initially, it's beautiful uh, and it's a classic kind of flow. There is no interaction between each filament of the streamline, but as it crosses somewhere, it breaks down and it forms a chaotic kind of turbulent flow, as you can see in this diagram. This is called a turbulent flow. Such flows also happen over wing surfaces in some conditions, and which lead to different phenomena, which we are going to learn about it in detail. Okay, next is a very simple two-dimensional flow. I have shown an aircraft with a wing, and just imagine as the aircraft is flying, or when the air is flowing over the wing, if they were to follow an absolute straight line, then the flow would be just about in two dimensions. That means from one point ahead to another point in rear. That means it's not going to curve, it's not going to turn or changes direction, etc. So this is called a two-dimensional flow. This we need to understand this so that we will understand the other phenomena much better. Okay, we talked about two-dimensional flow, but in reality, a two-dimensional flow is a theoretical concept. Very rarely can we have do we encounter two-dimensional flow. Most often, why most often? It's all the time. Flows are always in three dimensions. Therefore, uh, of course, we need to understand how it happens in two dimensions, so we will be able to understand the three-dimensional flow better. Anyway, here I have shown a three-dimensional flow. What happens is the airflow over the wing, it doesn't follow a straight line. It follows a curved line. As here I have shown over the wing top surface, the airflow is curved towards inside the fuselage, and it is curved at different angles at different point in time. Why it happens, how it happens, and all is a point of subject of study in our future. But at this point, it's enough if we do understand that its flows are always three-dimensional, and due to which there are several other issues which we need to understand. Here I have tried to show another phenomena. It's called the wingtip vortex. As I talked about airflows which are being three-dimensional, which gives rise to several other issues, as I have shown. Over the top surface of the wing, we saw that that flow is flowing towards the fuselage, and similarly, toward in the bottom surface of the wing, it flows outside the fuselage. So, what happens? Uh, as you can see in this diagram, which I have tried to show uh, in the rear of an aircraft, as viewed from the rear, this flow around wing tips, you can see it is anti-clockwise on the right side, because of its the three-dimensional nature of the airflow. So this is what the wingtip vortex is formed, and the vortex, of course, is increasing in size, and it goes down below. And we are going to learn how it affects the flight, and how it affects the other forces in a straight and level flight, and all that. But at this point, it's enough if we know that something called the wingtip vortex. We have been seeing different types of airflows, and we have touched upon a little bit of characteristics of each type of airflow, and how it's going to happen is what is our and how it is we are going to study the generation of lift and other forces during a flight is the subject in the immediate future, which we are going to learn. Anyway, that airflow, nature of airflow is very important, as you would have seen, and that itself it varies upon several other factors, whether the airflow is at low speeds, the shape of the aircraft and its attitude relative to the free stream flow, and the size of the aircraft, the density of air, the viscosity of air, the temperature, and the speed of airflow. There are several factors which are affecting the airflow characteristics around the fuselage, and thereby the forces which it's generating. So it's a complex it's a complex subject, and these phenomena are studied in something called wind tunnels, in which model aircraft are made, and they pass through huge amounts of air, and then they study the pattern of the flow. So all this is since there are so many variations, all this is summed up in one number called Reynolds number. So we are going to learn about this also in little bit more detail. So at this point, we need to understand that airflow characteristics can change with respect to different parameters, and it can give give rise to different characteristics of aerodynamic forces. So that's what we are going to learn. So this is where we end our class on this airflow theory per se, and we will move on in our next class to integrate what we are learning to see how lift is being produced, etc. Okay, here we come to the end of the class, and I hope we are able to introduce the subject of airflow uh, to its importance that it deserves. I hope you all enjoyed the class, and we will learn about the next few steps, how this airflow is going to affect several other things. So, never mind if you didn't grasp some of the concepts. We are going to learn about it more and more as we go further in the series of lessons. I thank you all for going through the lesson patiently, and please feel free to follow my lessons on my YouTube channel and my, of course, website, and offer your comments, constructive comments on the mail ID given below. I thank you all and hope you will enjoy my future lessons on the subject, and which there's going to be one whole lot of them.